And we're back with another episode of Solidity Fridays. Last week, we had Emilio on to discuss Aave V3 and Aave's general progression to get to V3, but we ran into some technical difficulties. So we're going to attempt that again this week, and hopefully it goes smoother. Emilio, welcome.
Hey guys, nice to be back. Yeah, we're having a good time last time, so let's try to pick up where we were the last time. Yeah.
Yeah. All right. So, as we said last time, very impressive number at the bottom. almost $22 billion in TVL in Aave across 7 networks. Tell us how you got here. How did it start, and how did it get to this number 22?
Yeah, sure. Well, actually, this number, like at some point, was higher because I think we reached at some point 30 billion market size. But back in the days, we were giving in liquidity mining 5 times more reward, essentially. So like the community has been winding down like the emission of the liquidity mining over time, but we retain most of the TVL, which shows essentially that. And actually now we are in the growth phase again. If you look for example at the chart of DeFi pools or whatever, this is because like we are expanding with V3 to many other networks. The listing of STETH by Lido brought another 2 billions worth of capital within the Aave protocol and stimulated more borrowing demand. And I think there are many more interesting stuff coming from both the Aave company, the community, and also from teams outside of that work together with Aave. I can think, for example, the balancer. There's some alpha right here. The balancer, like the boosted pools, they integrated they plug in directly in Aave to boost the capital while at the same time retaining low transaction costs because there is essentially funds manager that moves in and out the funds of Aave to ensure that there is always enough liquidity for trades, while most of the capital generates interest in Aave. And that is like right now, they balancer moved to a VBAL model. So it's giving quite high APR in terms of liquidity mining. And those are built directly on Aave, and they are also working. There will be also some work done to implement like LP shares as collateral. So this will probably also bring a bit more volume back again to the AMM market, which after the move to Uniswap v3 kind of declined in usage because, as we know, Uniswap v3 does not support like tokenization of the liquidity provisioning, essentially. So at some point, this number was higher. Like my personal goal is to have 100 billion by the end of the year. Let's see if we can make it or not. Like I think we can do it because there is a lot of stuff coming, and there are a lot of interesting ideas being built. There is also, like I mentioned the last time, the discussion about the new Aave tokenomics that just started within the community, and I think that can be a strong boost for the propelling like the usage and the TVL of Aave in the next months. From a technical perspective, how we get here, like the last time we did kind of a throwback of everything that happened in the past. Like when I joined, like we were working on Itland, the nature of Itland as an app, and as well, Itland was not really a protocol, not really designed to build on top, was more behaving like an app, but and it was peer-to-peer. So It gave us already in 2018 and 2019 a lot of experience to understand like the market, to understand the user needs. And this essentially brought Aave v1, and then Aave v2 and v3 are evolutions of the initial concept. They retain, from a technical perspective, some of the ideas that were actually launched in Aave v1. I think of the A tokens, which are actually enabled afterwards, for example, in v3, the creation of the portals feature. But like they are renewed, like v3 is renewed in almost every aspect. It still retains some aspects of the protocol architecture of v1, but it's new in almost every other aspect. So yeah, pretty excited moving forward, and like really looking forward to see this number grow even more than it's been right now.
Awesome stuff. There's an interesting point here where you bring up this 100 billion number. That seems enormous compared to the 22 billion. Is there, for the capital to reach that level, is that just rebalancing within DeFi and from other protocols? And potentially, I guess, the assets themselves increasing in price? Well, that's part of the question. But where does the capital come from? Is it just from within the DeFi system rebalancing towards Aave, or is there some larger strategy to bring capital from outside of crypto and outside of DeFi onboarded into the system?
Well, I think that for sure, like what I expect and what I hope will happen, there will be some rebalancing of capital from other protocols within Aave for two reasons. Reason number one is that we are working in Aave to kind of generalize the concept of the protocol from a protocol where you can lend and borrow money to a protocol where let's call it, like we call it, a liquidity protocol. So it's not just only the lender borrow. We are trying to build more use cases where that can eventually generate over yield over time, so that the protocol allows to use the liquidity that we provision to Aave in a trustless and decentralized ways, and at the same time generating more yield than what the simple lending would generate. Portals goes this way, eMold goes this way, and I think there are other use case in development and like other features in development that we will see in the next months that will generalize the concept of Aave as a protocol where you can invest your capital and expect a yield coming from different use cases and different sources. So there is another important aspect that we are going more towards this has more of a technical ring to it. And is like the second reason is that we are clearly moving towards a multi-chain world, right? Where essentially the idea is to onboard users not only on Ethereum, but on different networks and on different rollups built on top of Ethereum. Ethereum at the beginning worked great. At some point, it was a huge bottleneck for us. And this is when it was decided eventually to expand to Polygon and then to other chains. I love Ethereum, to be clear, Ethereum. I am an Ethereum maximalist, like completely. And like Ethereum was my first love. I will always try to bring as much value as I can to Ethereum. But I also recognize that it's nice working with other participants of this market, of this ecosystem. There is a lot to learn, and there is a lot to bring to the users. And this is why at some point, like, it was decided, okay, let's try to expand to other networks. Let's try to expand to Polygon. And it actually worked pretty well. And now there is the rollups that are finally picking up, and I cannot wait for that, because rollups open up other possibilities that are actually kind of limited or precluded to us in other L1s like Ethereum, like or the various side chains that are available in the market, because rollups on rollups computation essentially doesn't cost anything. It's the biggest part of the cost. Biggest part of the cost is the cold data storage on L1. So I expect that on rollups specifically, ideally, all the capital that is provided to other protocols should be supplied to Aave under the hood, because composability doesn't cost anything anymore. On Ethereum, for example, we were doing this with Curve, and at some point it had a lot of traction, the Aave Curve pool, because Curve was, people was providing capital to Curve, it was depositing in Aave under the hood. But this proved to be problematic on Ethereum L1 because of the increased transaction cost, which was affecting the swaps between stable coins. So swapping in the Aave pool was costing way more than a normal swap in the 3 pool contract because of the need to withdraw and redeposit. Essentially, this kind of faded out over time and lost interest, lost traction. And this is something, the Curve is only one example, but there are many other examples out there. This is one example where when we are at the point where composability doesn't cost us anything anymore in terms of computation, then we can really build stuff and bring capital to Aave, which generates yield automatically under the hood. So I think this is to say that I think there will be some capital relocation to Aave, but we are also looking to expand to other users. So multi-chain expansion is one of those, being present and capture more users across different chains. And also opening up to different use cases. There is a market for real-world assets that is picking up nicely. It's already past 20 million. There is ARC, which is a protocol similar to Aave, but for institutional investors, which is already close to 50 million TVL, I think. And those are picking up nicely momentum, and I think they open up to different use cases, different possibilities to bring capital to the Aave protocol. And also, as I mentioned before, there are many other new things being built by the company, by the community, and by other teams. So that is the goal, essentially. Try to be in the catalyst to bring capital within Aave and generate yield for users, leveraging different networks and different use cases.
Awesome stuff. To try and segue a little bit into the code, should we take a glance at the architecture and then get into one of these repos?
Yes. Let's do the last time we were talking a bit about the evolution of the architecture. I think how it evolved from V1 to V3. I think we can pick up from there. Yeah, we were looking at this diagram. This diagram is actually the V2 diagram. We were discussing the last time how we went from Aave V1 to Aave V3 and how it evolved in terms of implementation and in terms of architecture. So I think we can pick up from there. So essentially, one interesting aspect of the architecture of the Aave protocol that has been retained from V1 to V3 is that if we compare the architecture of V1 of Aave to the architecture of Compound V2, for example, those are quite different. If you look at the diagram of the contracts, they are quite different. Specifically, if you look at Compound, you have one contract that essentially maps every asset that is supplied to the protocol, So for USDC, you have CUSDC. For DAI, you have CDAI. For ETH, you have CETH, and so on and so forth. This means that every time you need to list a new asset, you need to add a new contract to the protocol with which users will interact. In Aave, we use a different strategy. So you have a single access point that is the lending pool contract. In V3 is called pool, is not lending pool anymore. And so all the interactions with the user happen at this contract level. So in Compound, actually, there is the controller that under the hood coordinates all the different. So we have CDAI, CUSDC, CETH, and then you have the controller that is, I think, never called directly, or maybe it is for liquidity mining. I don't remember right now, but still, it is usually mainly for coordination across all the different contracts. In our case, we have the pool contract, and the pool contract kind of works as single access point for all the interactions of the users with all the possible assets. This has many advantages, a few disadvantages. Like for us, when we design this architecture, like the advantages overweight the disadvantages. So I will talk about them a bit. The main advantage is that when a user interacts with Aave, they always interact only with one individual contract, which might not seem a big deal, but from a UX perspective, like if you care about security, it is a big deal, because you can tag, for example, in MetaMask, or can be an ENS associated with the pool contract, and then you are guaranteed that you are, even when new assets are listed or whatever interaction you want to do, you will always interact with the same contract, which is not the case for the Compound architecture. So from a UX perspective and a security perspective, is better for the user, because the user becomes familiar with the address of the pool when you see it popping up on MetaMask for submitting a transaction, and you can immediately see if you are actually interacting with the right contract, or maybe you ended up, for example, in a phishing website where it looks exactly like Aave, but is trying to steal your funds. This is a common occurrence, unfortunately, and this kind of helps, in my opinion, with this particular case. Another advantage is that it is much easier to integrate. This is something that I get very often, that integrating Aave is super simple, because you just need to point to the pool contract, code your main interactions, and that's it. You don't need to do anything else, essentially. If a new asset is listed, you get it right off the bat. You might need to enable just on the front end, for example, but you don't need to do anything. This is true also for liquidators. So if you want to plug in your liquidator, you just need to interact with the lending pool contract, and then maybe just when a new asset, if you want to start liquidating a different collateral asset, then you just need to plug in your in your configuration the address, and that's it. While in Compound, you always need to update the code to interact with the different contract. It's not a huge difference, but it makes some difference in terms of integration. And our goal really has been always to make the life of the integrators easy. Now, for people that will probably try to integrate the A tokens, they are swearing at me right now, because a lot of people has problems integrating the A tokens. We will talk about this later, probably, but to be honest, there we kind of sacrificed on easiness of integration, because we believe that the fact that the A tokens are always pegged is really, really powerful, and it is something that in the future can come really handy. And for example, portals is one of the features that we built on top of this, that really shows how having pegged A tokens is powerful compared to having an exchange rate like other protocols. The third advantage that this architecture has is that it's really easy to add new functionalities and to have them on all the assets at the same time. So if, for example, in V3, there will be an upgrade path from V2 to V3, from V2 contract to V3 contracts. In V3, we added the permit function for the supply and the repay, and I think maybe we added the ERC 712 signatures for the create delegation. All of these three features, like you just upgrade the pool contract and you get them for free on all the assets. While in Compound, you need to go and upgrade all the different instances of the C tokens, essentially, to have a function that adds essentially a new feature per each asset. In our case, you just update the pool and you have right off the bat for all the tokens, essentially. So these are the advantages. The biggest disadvantage of this approach is that if you need a custom behavior for a particular asset, then in our case, it's much more complicated. So imagine that you have an asset behaves in a particular way for which you need a specific action on supply, then that becomes tricky. Listing that asset in Aave becomes trickier. To be honest, we never ended up in this situation until now. The A tokens, the accounting of the A tokens actually happens in the A tokens contract. So like if you need a particular accounting for a certain token, that can be done easily. It was done, for example, by Amplifort and Lido ETH. If you need a particular action, additional action on supply or withdraw or whatever, that is kind of tricky, but until now, it's been 3 years almost, and we never ended up in this particular situation. So I think it's going to be, it's not going to be likely that we end up with an asset that is, with a meaningful asset to list in Aave that cannot be listed because of this limitation. In a rare case, like eventually, if there is really an asset we cannot avoid to list, then a specific function can be added to the pool contract only for that asset. So in my opinion, this architecture has some advantages compared to the current Compound architecture, and this is why we choose this way in V1, and we kept it in V2 and V3. And this is also to avoid disrupting the work of integrators and people that is building on top of Aave. This is also another important aspect, because if you look at the architecture of V1, V2, or V3, you can see common denominators, and you can see, architecturally speaking, they are kind of similar, and the interfaces we kept. We even kept, like, if you look at the code, there are some kind of compatibility functions for the interface to avoid breaking an integration moving forward to the different iterations of the protocol. So unfortunately, this kind of makes, in some places, the code a bit dirty, something that I don't particularly like, because for V3, honestly, I would have liked starting completely from scratch, but this was, and like there are some aspects that I don't particularly like that we can't inherit from the first version, and I would have loved to change, but we didn't do it because we wanted to avoid disrupting the work of integrators. And another reason is that this architecture works. I mean, we have seen on like in real life that it works. It is safe, so like this is also another important point. Of course, like starting from scratch is cool. It allows you to gives you more margin to improve on what you built in the past. But at the same time, like starting from scratch means that you need also to start from scratch on security, which is for us is paramount. You know, like it's super important. Security is like the most important aspect in everything that we build in Aave and in the Aave community, and it's essentially something that always has the priority. So even though some parts of the code I don't particularly like, I would have changed it in some other way, or some part of the architecture I don't particularly like, we choose essentially to not rework everything from scratch, but to keep like a certain continuity between the versions, because this allowed us to retain parts of the architecture of the code that are clearly safe, because knocking wood, like in 3 years, we never got hacked. We had some security issues, unfortunately, but that is, I think, kind of inevitable. So they are safe, and at the same time, like they allowed us to retain everything that we built over the years in terms of testing. This is another super important aspect for me. Like the most important part of the protocol is not the code of the protocol itself, it's all the testing infrastructure. Like we spent way more time in writing the tests than writing the code, and like the ability to keep the continuity between the test infrastructure and the test suite that we had in V1, and growing it over time and bringing it to V3 and still use that, was super important. It saved us a lot of time. And since those tests worked in the past, because like the protocol was safe, we kind of retained the same level of security, at least for the core functionalities, for the same functionality that are common between the different instances of the protocol. For example, we built we built a predictor in the test. This was built for V1. So if you look at the test of the code of the test, like there is a predictor that is built in TypeScript. Some part of the code is a bit messy, I will be honest, because like the effort to maintain the test suite is even way bigger, actually, because it grows exponentially, the fixture and everything. So it makes really it's even harder to keep a very high code quality within the test suite, but it works really well. So this predictor essentially it allows us to write scenario in JSON format, where there are different interactions of the protocol, and then this predictor executes these scenarios against the protocol and against a predictor that we wrote in TypeScript, and then compares the results. And then it allows us to check, okay, when one of the two is not the expected, like we need to understand where the bug is, if it's in the predictor. This is a really common way of testing and ensuring that like what you build it actually work, is rebuilding it with a different technology and compare the result. So you usually see whether you find the problem in one or the other, it allows you essentially to verify the validity of the model that you built. And this also allowed us to test edge cases that were very, very complex to test individually and independently, and also cases that were hard to test using formal verification or fuzzy testing. So we retained all of these over the years between V1 and V3, and this essentially is the reason why the V2 or V3 are like V1, V2, V3. They are an evolution of the same concept, of the same idea, rather than a complete rework that like would have changed like the architecture and the code base much more substantially. Yeah.
Awesome. Yeah, so much to unpack there. Will, are you interested? What you were saying about Emilia, what you were saying about the tests, there was very interesting. That you've got some TypeScript system that you set up scenarios in a JSON format, and then it'll just run through those scenarios and run the tests on them. Will, where do we go from here? Should we get into some contract code or some test code?
I would go on the contract code first. Like we can go, like for example, we can go to V3. Last time we also talked. I think we can do a peek like how the code has been differently organized in V3. Like if you go on the V3 core, for example, package, on the repo, sorry.
Okay.
Yeah, you have the here. Yeah, because so you can see like in V2, this is one interesting. The first interesting aspect is that in V2 we had a kind of a monorepo, like where everything was in the same repo, deployment scripts, periphery contracts, core contracts, tests, and so on and so forth. And this kind of was hard to manage, especially because of all the PRs coming in from different teams, from contributors, from the community, listing assets, new deployment to different networks, and so on and so forth. It was really complicated. So we took inspiration from Uniswap in the idea of organizing the code. So we decided to split the code from the monorepo that was before in V3 core, V3 periphery, and V3 deployment that is currently not public. It will be made public after the rollout of V3 is completed. And right now V3 is still on with training wheels, so it's like growing slowly because like there are limits on how much the market can grow, because of course we want to battle test it a bit before. So we took this idea from Uniswap and we split the core contracts, the periphery contracts, and the deployment scripts. So right now, like if you want as a community contributor to add scripts to deploy to a different network, you go to the deploy package and you just add a TypeScript file there with the types and then the definition of the objects which define the configuration for that particular network. You run a script and that's it. Like it's super simple to deploy to different networks. The periphery contracts, which include contracts that are not strictly related to the core functionalities, they are in a separate repo. Periphery contracts, we can, for example, you can go to Treasury, to the Treasury folder, and here there are the two contracts that essentially collect the fees from the protocol, and they store in the collector, for example. It does all the function to move funds in and out of the system. The collector controller allows the governance to control the collector and do management of the treasury. Yeah, it's really simple. You can go down it's just like it allows the collector to approve, to transfer, and so on. This has been made because the collector is proxied, so like you need a controller for the same entity to control and allow the contract to be upgraded. This is an interesting topic that I want to discuss, because sometimes I get on Twitter a hard time because like in Aave we use proxies, which is fun. This is something interesting because regarding proxies, I think that they are useful. They are not necessarily evil like many people think. They are a useful tool for maintaining the possibility for a community managed and governance controlled protocol to still add features. For example, we will be able to upgrade the contracts to V2 from V2 to V3 because because we use the proxies. Without the proxies, we wouldn't, even with a modularized, the differences between V2 and V3 are so important in terms of code organization and logic that probably with a modularized infrastructure with immutable contracts would have been still very complicated to maybe some features you would be able to migrate to V3, but not like the important rework of many features that was done from the evolution from V2 to V3. So regarding the proxies, going back to the concept, as I mentioned, for me they are a useful tool that needs to be managed the important way is how you handle them. So it is true that in Aave we heavily use proxies, and this kind of have the drawback that unfortunately they add a bit of gas in the user's interactions. At the same time, they give the possibility and the flexibility to the Aave community, the developers that work on Aave and the Aave governance, to add and change features more easily. I would not say more easily, because even with a modularized protocol, you can do it as easily, but more extensively. So you can do more extensive changes, which of course comes with the drawback that you need to be very careful when upgrade the proxy. But also, like, we manage the proxy in a very modularized way. I mean, Aave is really modularized. So, like, actually, if you want to upgrade a contract in Aave, you never interact with the proxy directly. There are contracts that are handle the instantiation and upgrade of the proxy themselves. So if you want to create a governance proposal to upgrade an Aave token, you just need to pass the instance, but you never interact with the proxy directly. It is the protocol that manages to upgrade the proxy, call the initialization function, and hides the details of the proxy from the user that is trying to update the proxy completely. So, for example, all the tokens that are A tokens and DEP tokens that are upgradable, they are managed by the controller. This is in the V3. You can go, for example, contracts, protocol. I think pool should be. No, I don't remember correctly. Pool configurator, yeah. So, for example, if we look at the pool configurator and you go to add init reserve, I think is the name of the function.
Init reserves?
Yeah, init reserves, this one.
Yes.
So it calls a configuration library. This is also another interesting aspect that I will talk before. But this execute init reserve actually takes care of instantiating the proxy, initializing the proxy, and you just need to pass the address of the implementation, and takes care of everything. If you want to upgrade a token of that particular reserve, then you still go through the configuration. There is an upgraded token function. And so all the details of the proxies are completely hidden, like the caller, then the entity that wants to upgrade the contract, for example, through a governance proposal, doesn't need to care about the details, who owns the proxy, what to call on the proxy, and so on and so forth. All of this is completely hidden by the configuration, the configurator for what regards the A tokens and the tokens. And the addresses provider is the kind of module manager that manages all the major modules of the protocol. So you have the pool, you have the configurator, you have the treasury. All of these major high-level components are managed by the addresses provider. So when it is true that we use proxies, the way we use the proxy is to completely hide the details of the proxies themselves to the entity that wants to upgrade the contracts. Of course, the implementation, like all the complexities related to proxies remain. So, as mainly the preservation of the storage layout. So, if you upgrade a proxy, you always need to be careful with the storage layout. So, this is something that is still on the side of the upgrader. I mean, the person that is upgrading the entity that is upgrading the contracts. I think in certain, depending if you have a fully modularized with mutable contracts and like a command pattern implemented in a router kind of contract where it calls different modules depending on the interaction. In general, you have the same issue in the sense that a module, if you either pass everything to the module or use delegate call. If you are using delegate call, you need to be mindful always of the storage layout in any case. So when you deal with contract grades, there are always pros and cons in any particular architecture. The idea behind using the proxies is that we are so early in this technology that I am not really able to predict what users in the futures might need, and because of that, I cannot really predict what features we might need to add to the protocol. And in this case, proxies give maximum flexibility. Some people will not like it. I understand perfectly, but in my opinion, it's still something that is worth having in a protocol that is supposed to evolve, still evolving. We are still a long way to go until this protocol can become immutable. We are going there. We can talk about this later. Some features that we added to V3 actually try to go towards a path of governance minimization, but it's still too early. So this is why it was decided to use proxy in the first place. I think we can go to the main contract, to the pull contract, and discuss a bit how we reorganize the code in V3.
All right, this one, pool.sol.
Yes. Yeah.
I see there's another L2 pool.sol that will be interesting.
Yes, that is also interesting. We can talk about it. Yeah.
Okay. So where do we go from here? Should we just?
We can go to the base interaction, like to the supply function, for example.
Okay.
Because first thing that I want to discuss, supply here. This is supply with permit. This is fine. Yeah, this is fine as well. Okay. So the main thing I want to talk about here is that, as you can see, we used every action. There is no actual execution code in the pool contract. One of the biggest issues that we had in V2 regarding the way we wrote the code is that we were very close to the contract size limit in the pool contract, because the pool contract was importing all the libraries, and of course it was also had some execution code. Therefore, the code of the size of the pool contract was quite big, and the first problem that we had to face when we started with V3 was that, okay, we need to rework the architecture in a way that the pool contract is not as big. Here, we could have used modules, like in the more common way that people refers to modules in the Solidity development space. We decided to use to split the code in very modularized in libraries. So each group of action, each action that has a certain responsibility is grouped in logical modules. For example, the supply logic contains the logic for executing the supply action and the logic to execute the withdraw action, and I think others. The borrow logic has the logic to execute the borrow, the repay, the swap rate mode, and so on and so forth. Then there is the flash loan logic for the flash loans, and there is the liquidation logic for the liquidation function. So, what we decide to do is that, splitting the code in different libraries that essentially allowed us to modularize further the code and have functions separate logically by concern. So the supply part in one side, the borrow part in one side, all the validation code that validates pre and post conditions is in another library, separated, so that essentially in the pool contract we just imported the libraries and invoked the libraries to execute. You can see borrow logic. Invoke the libraries to execute the particular action that the pool needs to execute. These are some advantages again and some disadvantages. The main advantage is that this allowed us to split the code quite importantly. Each independent library is relatively small. The pool contract is super small. In fact, we were able to use 200,000 optimization runs, while before we were limited to 200, and we were already close to the contract size limit. Now we use 200,000, and we are nowhere close to the limit. So For the purpose of what we needed, it worked pretty well. The second advantage is that it's relatively simple because you can see immediately, like when you look at the code of this function, you see, okay, the execute, the borrowing logic contains all the code relative to execute, borrow, and repay, and everything else. So it's pretty easy to understand, pretty easy to read. This is also an important thing. Like we like code that is super easy to read. Like we tried our best to make the code as easy to read as possible. For two reasons. This favors security because like the code that is harder to read, it takes more time to audit, and it's more prone to errors, and those errors are harder to be seen. And like second reason is that integrators often like they need to look at the code and understand what is going on. And if it's really, really hard for integrators to understand what is going on, then they come at you and ask questions. And if you have 500 integrators to manage, 500 people asking you questions all day, you are never going to work again. Essentially, you're just going to spend your time trying to help integrators going through the code. This is why I believe, for example, if we look at our code and Maker code, for example, the Maker approach, I like it, but I also recognize that you need to study to understand like the terminology. It's like learning a meta language. You know, you need to learn all the concepts that they use within the architecture of the code before being able to understand the code. This makes me think that this code that is not really designed for people to build on top of it, because, and it's actually true, because like not because they didn't want people to build on top of the protocol, but because of the design of the protocol, like you can essentially only create a vault and supply collateral and borrow, while in Aave there are many more interactions, you know. So Aave is more designed to be kind of a base layer for liquidity, while Maker is a protocol to mint a stablecoin. So that's quite different in terms of use case. So I can imagine that an integrator going deep on what is happening to Maker needs to spend a lot of, I did spend quite a bit of effort in understanding and I still don't understand like completely, because I didn't put that much effort. You know, you need to put a lot of effort in the to learn the terminology, and learning the terminology and learning the meta language allows you to understand like the architecture and the code. In our case, we wanted to have it as simple to read as possible, because if something goes wrong in a function, an integrator needs to understand immediately what is wrong, rather than they need to ask questions that also need to be answered. So you need to spend time. And this essentially saves time for both us and the integrator that's trying to integrate the Aave. So you look at this function, you understand immediately the logic you are looking for is in a specific library. The other advantage is that we can modulate. We can easily modulate how big we want the pool contract to be. So if we want reduce gas impact on the execute borrow, we just go and make the execute borrow function internal. This will add the code to the pool contract and avoid the need for another external call, so it will save a bit of gas. And this is true for all the functions. There are networks where there are no constraints in terms of code size, so you can make everything internal and save further amount of gas for the users. The disadvantage is, as you can see here, because we don't use delegate call, you need to pass a lot of parameters to the other side. It has not been a huge, it has been like something that I don't particularly like in this case, because passing a lot of parameters to a function is more error prone than just like, if we didn't have to pass the state, essentially the whole object data types that you see here, we would not pass it at all, because it's automatically inherited. But At the same time, it is kind of the drawback of using libraries. So at the end of the day, it was not a huge deal in development, and as always, I think the advantages like overweight the disadvantages. So, for example, we can go. I don't know. We can go through the supply function if you want, just to give an idea of how the code is organized, and then I think we can go to the more interesting parts of the code. What do you guys say?
Yeah, I mean, sounds good to me. William, what do you think here?
If you guys have any questions, also well, feel free to interrupt me and ask because.
Supply sounds fine.
Okay. Then we can go to the supply logic.
Okay, so we go back here. No, here, and then
it's libraries, logic. Yeah, supply logic.
Yeah, interesting.
Okay, so you can look for supply function. Should be the first one, I think. Execute supply.
Sorry, that's an event.
No, it's the event. Yeah.
Execute withdraw. Did I pass it? Execute.
Yeah, execute supply is this one. So yeah, if you can center it, so like I have all the code because we go a bit above, I think.
Oh, sorry. There we go.
Yeah. Okay, so like if you look at the code of the execute supply, you can see a pattern that we use kind of everywhere. So there is the validation. First step is always update of the state of the protocol. Update state means for people who is not like so familiar with how these kind of protocols are implemented, essentially the interest generated is always accumulated through a storage variable that we call index. So essentially, we calculate every time an action is performed on Aave, and the same concept is used on Compound. Every time an action is performed on Aave, there is an accumulation of interest that happens between the last action and the next action being executed. So what happens is that the protocol calculates how big this amount of interest is and essentially accumulates to an index that tracks the yield generated for everyone within the protocol. So every time capital is accrued to this index, essentially it's in the it's stored, it's accounted, it's in the accounting is stored that X amount of capital has been accumulated as yield. So essentially update state does the update of the indexes that keep track of the yield on the supply side and on the borrow rate, on the borrow interest on the borrow side, and also it redirects, calculates how much the protocol has earned from the interest since the last time, and accumulates this value in a storage variable that is specifically for the treasury. Then there is a function that allows essentially to mint the A tokens in the corresponding amount accumulated in the storage variable to the treasury. So the treasury receives a token. So this is the first action. This is a pattern that we use everywhere. Then there is the validation. So the logic, the validation essentially validates that the action can be performed by the particular user in this particular moment. For example, in the case of validation, we check that the user is trying to supply a proper asset that has been activated and configured. We check that the reserve has not paused. We check that the amount is correct. So, for example, it's not zero. I think we check if the amount is not zero. I don't remember, so probably. So the first step is updating on the state. The second step on validation. The third step is update of the interest rates. So because every time there is accrual and there is an action, so withdraw or borrow, whatever, the interest rates needs to be updated, because this changes the liquidity available. And if the liquidity available changes, of course, in Aave, the interest rates are decided algorithmically. So this changes the interest rates as well. And then there are, in this case, there are external interaction, which is the safe transfer from, and then there is the mint of the A token. This is peculiar because like here we are breaking the checks effect interaction on purpose, because we actually verify that in this particular case, the check effect interaction made things worse in the sense that you are giving collateral to the user before essentially the actual capital was moved in, which essentially means that if you re-enter, you already have capital, so you can do stuff. You have already collateral. You can do stuff with your collateral, like leveraging your collateral your deposit multiple times, and have leveraged A tokens within the protocol, within the transfer. So your transfer is still not finished, but you have collateral. So if you list an asset that is, for example, as a reentrancy, you could do nasty stuff in this particular case. So we decided to do the external interaction before, and then after the external interaction, you receive the actual collateral. So this allows for less manipulation. Why this works and is not subjected to a reentrancy is that because we don't use any fetched state that comes before the external interaction. For example, if this is first applied, this Boolean was being read before the external interaction, probably there already would be some issues, potential issues of reentrancy. But we are not using any state that was read before the external interaction, so there is really nothing for an attacker to use here, essentially to manipulate afterwards in a reentrancy occurrence. So this is why we are breaking checks effect interaction here, because in this particular case, it actually made things worse. So, but usually in all the other interactions, we do the accounting first, and then we do the external interaction to avoid breaking the checks effect interaction. So in general, it's except the supply function. In general, there is interactions, so accounting essentially, and then external interaction. As I mentioned in this particular case, the mints come afterwards. So after the transfer, the user receives an equivalent amount of A tokens that are essentially mapping one-to-one what the user has correctly deposited. And as we know, like the mechanism of the A tokens, it starts to accumulating interest right away after the user has deposited. Then, like essentially, there is a further validation. There is a post condition, and not all the functions have a post conditions. But in this particular case, because we have the isolation mode, we need as a post condition to check if this is the first supply, if the user can actually use the particular asset that is trying to deposit as collateral. Because of isolation mode, the user might not be allowed to set an asset as collateral. So in that particular case, this helps with the isolation mode. Is a feature we can talk about it later. So this kind of highlights how the architecture works, how we kind of design the code to be kind of consistent across all the actions. In general, there is update of the state, the validation, the update of the interest rates, sometimes there might be some operations in the middle between these two, because the borrow rates, for example, need to be calculated between the validation and the update of the rates. Then there is accounting, and then there is external interaction. So on overall, we try to use this strategy everywhere. I don't know, do we want to go, for example, we can talk about the new, do you guys have questions?
I mean, I don't have immediate questions. It's like I'm just sort of like kind of blown away by how much thought is put into like every piece of the protocol. There's like so much to unpack. Will, do you have any questions?
Truth is, just maybe to dive into like kind of a specific detail. If you're taking a look at the execution supply function, so the first two arguments are mappings. I seem to remember we unpacked this on a different call, a different Solidity Fridays, maybe the one on Lens even. I'm trying to remember how passing mappings works as an argument.
I think, if I remember correctly, it just passed the pointer to the mapping. So like, you know how the mapping is stored, that it has actually, it just gives you the the position in a mapping is calculating using the
check hash.
Yes, the hash. Yeah. So it just essentially passed like the information that allows you to calculate the first position of the mapping, and like of the storage of the mapping, and then from there you can by indicizing as the compiler translates in the catch-up, and then you can like essentially just like calculate the positions.
So I guess I'd understand how an integrator in Solidity would call that easily enough. I mean, if they just implement the mapping on their end, I'm assuming they can kind of return that.
Yeah, well, the execute supply is not, it is external because it's a library. In this particular case, like we link the library externally because we want small sides of the pool contract, but this is not meant to be called externally. This is meant to be called by the pool contract. You know, so yeah, like you can call it because it's a library that is deployed separately and external, but you can pass whatever data you want, but it will not do anything and just change the code. So, but it's not meant for integrators. Like integrators, they are gonna call the supply function in the pool contract. You know, this execute supply is internal logic of the pool, essentially. So it is meant and designed to be called by the pool contract, and the pool contract, of course, has already all these data structures and
implements the same mapping by it. Yeah.
Yes.
Okay.
So,
interesting.
I mean, theoretically, since it's a library that is deployed independently for reasons of code size reduction, theoretically you could call it by passing compatible data from a contract that doesn't do. That is not necessarily the pool, but it will not do anything if not just executing the logic of the pool, essentially.
All right, so that would kind of avoid the next question then, which was assuming like I hadn't realized that this was only like kind of on the pool end of the logic, and that there was another user-facing function on top of it.
Yes.
I guess I was wondering.
Yeah, the user facing is like what I mentioned before, is in the pool contract. So the user always interacts through the supply logic in the pool contract, but then inside the pool, each function has a specific execute, like this one, for reasons of code size reduction, because the contracts cannot be bigger than 24 kilobytes. So if we put this logic, this code, all in the pool contract, it would be way out of the contract size limit, essentially. So it's split in libraries, and those libraries are external because, again, the linking otherwise would still make the pool too big. But they are meant, in this case, those are internal functions meant to be called by the pool contract. Yeah.
Do you know if there's anywhere where the mappings are used as an argument in user-facing? I guess part of what I'm thinking is like, I guess I can start thinking about how you would make a call like that out of JavaScript or something like that.
No, I don't think you cannot. Yeah, you cannot. Like you need to pass. You cannot pass mapping of storage from JavaScript. You need to call like. What you can do is you can pass memory structs with the ABI encoder v2, but not storage. You cannot call this function from JavaScript, for example. Yeah, it needs to be.
I mean, if it's just the pointer, you'll be able to just kind of catch through it. I don't remember the exact spec for the for getting the pointer, but it's something like what is it? The signature, the signature and the value of the key or something like that hashed together, like hashing the signature, then hashing that with the value of the key. And it should be possible to replicate that in the JavaScript library.
It could be, but I'm not sure. I don't think the ABI encoder now, like I'm not completely sure. I don't think the ABI encoder allows you to call a function that has a mapping of storage mapping as a function. So that is the problem, I think. But to be honest, I never tried. So like I would need to go back and try, because I'm not completely sure. Yeah.
Interesting. So yeah, that's all I wanted to ask.
Yeah.
Awesome. Should we? Where should we go from here? You said that there was some.
I think another interesting thing that we can talk about. Let me think. We can talk about, for example, one interesting thing that we did with V3 is the usage of bitmaps to essentially perform like some important operations. For example, E mode and isolation mode, they heavily we actually introduced this in V2. Essentially, in the protocol, we need to track every user position, like to understand what the user has supplied, what the user has borrowed, and so on and so forth. And also the reserve configuration. So every time an asset is activated on Aave, it has some certain configuration, the liquidation threshold, the liquidation bonus, the reserve factor, and so on and so forth. All of this, to store this in V2, this was introduced originally in V2, and the usage was extended in V3. We decided to use essentially a bitmap. So you have a uint 256 that tracks. You can go, like, if you go back to libraries, to the libraries folder.
Libraries.
Yeah. There is configuration. And there is, for example, user configuration. So user configuration is a library essentially that tracks what the user is borrowing and what the user is supplying at any point in time, right? So you have a uint 256 to track essentially the user position, to track each user position, and to track what the user is actually supplying and borrowing. So the first, again, as usual, this has some advantages and some disadvantages. The advantage is that this is really, really cheap and really, really efficient to query, because like you can do complex query by doing bitmap tricks, essentially. So if you want to know, for example, if a user is borrowing or supplying any, you just check against the borrowing or the collateral mask. What is the value? And like if it's 0, it means that the user is not borrowing anything. And also there is the advantage is that you can do complex calculations to understand, for example, if a user is only borrowing certain assets or supplying certain assets, which is each something that we leveraged for isolation mode and E mode in a very gas efficient way. So the disadvantage is that since we use one single 256 to store what kind of assets the user has borrowed or supplied, this means that currently V3 is limited to 128 assets maximum that you can list, because otherwise there would be not enough space in the mapping to track more than 128 assets. This for us is right now an acceptable limitation, because like 128 assets is a lot of assets and would probably break the protocol in the sense that calculating if some user is borrowing and supplying all the assets, calculating what this user the total position of the user would be so expensive, it probably would be bigger than the block size. So more than 128 assets would expose to this particular use case where a user could break his own interactions by borrowing and supplying all the assets, for example. In the future, if we want to expand to more assets, this is still possible, because the user configuration map is stored in this structured data types user configuration map that you see here, where there is one single EUN 256. Since this user configuration map is stored in a mapping, you can always essentially add a new EUINT to the struct, and this would not cause any issue with the storage layout. So why we choose this approach of using the bitmaps to track the user position? Because essentially we did some simulations. Like the other alternative that I think is used by Compound would have been to use a list. So you have you keep essentially an internal list of assets that the user is borrowing. So you need to track. To query the list every time you want to understand if the user is borrowing something, if the user is borrowing something, and what the user is borrowing. This is as cheap as this implementation for some cases. For example, if you want to check, like if the user is borrowing, you just check the length of the list, which is still one storage variable. But it is more expensive in other cases. So if you want to check if a user is borrowing a certain asset, you need to check all the assets that this user is borrowing. So you need to traverse the list. And if the user is borrowing many assets, this can occur in many more slots, essentially. While here, you just check with the bitmap. You just read always. You store in memory the bitmap once. You read multiple times the same bitmap. You can understand almost immediately what assets the user is borrowing or supplying, for example. And also, as I mentioned before, it has the advantage that you can determine essentially what the user is borrowing or supplying with some interesting bitmap manipulation tricks. Can you go down? I think there is a function, is borrowing any, for example. No, is borrowing one. There should be.
See, is borrowing.
Is using as collateral, and can you go down? Is borrowing one. Yeah. So
there's also is borrowing any right under it. Yeah.
For example, if you want to understand if the user is just borrowing one, you don't need to traverse. For example, you can just use this particular trick that where n minus one is always zero if the user if because if the borrower is borrowing just one, the data that the user is storing that tracks the position, and the borrowing mask essentially gives you only the bits that track the borrowing position. So if the borrower is borrowing only one asset, it means that the asset will always be in a position where the end value is a power of 2, right? Because it's either going to be essentially, this is a detail I didn't give. Like in the mapping, we are storing the bits to track the position one after the other. So like bits 0 and 1 track the position for the user of asset 0. Bit 2 and 3 track the position of asset 1, and so on and so forth. The first bit tracks if the user is supplying as collateral. The second bit tracks if the user is borrowing. Okay, so when the mapping is filled up, and like the user in this mapping there is 1 1 1 1, it means the user has borrowed, has supplied everything. If the user has bit 0 to 1 and bit 3 to 1, it means that the user has supplied asset 0 and borrowed asset number 1. Okay, so essentially each position of each bit tracks as if the user is supplying something and if the user is borrowing something. So odd bits, odd is like I always mix up odd and even in English. So the even bits are like the collateral, and the odd bits are borrowing. Okay. So in this particular function is borrowing one, for example, we take this data mapping, we end with the borrowing mask, which essentially isolates the bit that tracks the borrowing. And those bits are always each individual bits is always a power of 2, right? So if the user is borrowing more than 1, it means that the resulting number out of this will not be a power of 2. So if the user is only borrowing 1, this number, the resulting of the end, will be a power of 2. So by checking this, essentially, we can immediately check if the user is just borrowing 1 or is borrowing multiple assets. So this is one of the tricks that we use to save gas and to perform computation on the bin maps. And this came particularly useful in 2 new features that we added to Aave, the isolation mode and the E mode. I will describe quickly what this function do because it's necessary to then explain how we implemented them. Essentially, in E mode, E mode is a feature where users are granted higher collateralization if they only limit themselves in borrowing certain category of assets. An example. What we noticed in Aave v2 is that borrowers of USDC, there were some borrowers borrowing USDT with USDC, for example, right? Why they were doing this? Because a lot of people back in the days, maybe now not anymore, but back in the days, a lot of people were thinking that at some point USDT would fail, right? So essentially, by keeping your liquidity in USDC and borrowing USDT, you are earning on your USDC yield, and you are borrowing a currency that if it fails and it goes to 0 because something happens, essentially you get a loan for free. So they were hedging they were leveraging kind of the risk of USD failing by using their capital and at the same point like compensating on the borrowing interest with the supply interest of USDC. But we noticed this had a problem because like the user is borrowing and supplying the same asset, is borrowing a USDT and supply USDC, and these 2 assets are stable relative to each other, but still the borrowers were limited to 85% collateralization factor, which is the collateral factor 80%. Collateral factor, this is the collateral factor of USDC. So out of your dollar of USDC, you could only borrow 80 cents of USDC, and this is not really capital efficient because in this case we can go much higher. So this was noticed during after the release of V2, and so this essentially made us think, okay, how we can work to optimize this edge case and to offer more capital efficiency. So we came up with this idea that is E mode. Essentially, E mode, like a user can enter, this is a mode that can be set by the user. So a user decides to enter the E mode. When it does this, it says, okay, you know what? I want to enter E mode. I want to have more capital efficiency for my collateral. And but I will limit myself to borrow only a certain category of assets. So in the particular example that I did before, using USDC as collateral to borrow USDT, the borrower could enter E mode and could essentially decide to borrow only stablecoin. In that, when the user does that, what the protocol allows is that if you're using as a collateral an asset that is in the same what we call category of the assets that you are borrowing, then you get higher collateralization factor. So in the example that we did before, if we had E mode in V2, the user that was borrowing USDT to and use USDC as collateral could have enabled E mode, keep using your USDC as collateral, but now it could enjoy way higher collateralization factor up to 99%. So theoretically, you can get 99 cents out of each USDC that you supply. This works because essentially it only grants higher collateralization to the same assets that the user is borrowing. So since these two have low volatility one against other, you can allow the user for that particular collateral to get higher collateralization factor. And this is really cool because, for example, we can use this for staking derivatives. So if you have ST-ETH and you have ETH listed in Aave and you want to leverage your staking derivative, you could choose an eMode category to borrow the eMode category ETH, and then you can use ST-ETH to borrow ETH with very high collateralization factor, and therefore you can leverage way more. You can have way more leverage on your ST-ETH up to 50x, for example, which allows you to leverage your earnings from staking 50x. This is something that will happen when we have V2 upgraded to V3 essentially. This posed some challenges because we were, okay, if the user is limiting himself in only borrowing a certain type of assets, then we need to understand at any point in time when the user is trying to enable eMode, what the user is actually borrowing, correct? So like if the user is already borrowing an asset that is not in that particular category, we cannot allow to activate eMode, right? If the user is not borrowing anything and the user wants to activate eMode, then the activation is allowed. If the user is borrowing something that is not in the category that the user has chosen, then we should not allow the user to activate eMode. If the user is trying to borrow something and the user is in eMode, it's trying to borrow something that is not in the particular category, then we need to revert in that particular case. We need to disallow the borrowing. This particular logic brought some challenges, like we need to understand what the user is borrowing and what the user is supplying as collateral to understand if we can actually activate eMode and whether or not the user has the right to have higher collateralization depending on the collateral. And we did a lot of bit manipulation to do this operation, and the bit manipulation happens on this masking that we are talking about here. Let me think if I remember the code right now. Can you go quickly to the borrow logic? Actually, not to the validation logic. I think. Yeah. It's in libraries again, and validation logic.
Okay.
Yeah. Can you go to validate borrow?
Validate supply, validate withdrawal, validate borrow.
Yeah, there should be at the end, I think, a check on the get borrowable in isolation, get eMode category here. Yeah. So, yeah. So if the user has activated eMode, right? We check in this particular check allows to verify that the configuration of the asset, which we call reserve configuration, is equal to the category that the user has chosen. Okay, so when the user tries to borrow, one particular validation step is, okay, is the user in eMode, which checks param user eMode category is different than 0. 0 is the default, which means that the eMode is not active. So if the user is not in eMode, this if skips altogether. If the user is in eMode, then we enforce that the asset that the user is trying to borrow is equal to the eMode category that the user has chosen. If it's not the same, then the code reverts with inconsistent eMode category. So this kind of shows the first check that I was mentioned before, that whenever a user activates eMode and is borrowing an asset, we need to ensure that this category that is borrowing is the same as the eMode category of the asset. An asset in the reserve configuration, the get eMode category is a configuration flag that stores, essentially, not a flag, a configuration value that stores the eMode category for the asset. If the category of the asset is 0, it means that it has no category, so it's a normal standard volatile asset like can be Link or RapidBTC, has not been categorized in an eMode category. So if the user has chosen a stablecoin category, for example, it's 1, and the asset has 0, which is volatile, you cannot borrow a volatile asset while you are in eMode. So this shows like the one of the checks that I mentioned before. Can you go to eMode logic, I think?
Okay.
E-mode logic.
E-mode logic.
Okay, here there should be, I could say something wrong because right now I don't have the code. So okay, sorry, it's still in the validation, also in the validation logic. Yeah.
Okay.
Yeah. Can you search for validate e-mode?
Validate e.
It doesn't find it. Can you search for e-mode?
Mode.
Yeah, there should be a validate e-mode somewhere. It should be in here, theoretically. Yeah, this is the checker we were talking before.
Validate replay.
It's mentioned in many places, unfortunately. No, so validate rate mode. Okay, it's validate factor. Validate set user mode. Okay, this was the name of the function here. It was not validate mode. Yes, it's this one. Okay. Let me look at the code quickly because this way there's some configuration. Okay, can you go a bit down, more further down? Yeah, it's actually what I was, okay, I can describe this as well, but the code I was mentioning is not here. But anyway, like this is essentially the validation code that it gets executed when a user tries to set essentially an e-mode category. So if the user is trying to set an e-mode category, we need to validate a few things. Can you go a bit up?
Yeah.
Yeah, here. So if the user config is empty, right, it means essentially that the user is not either supplying or borrowing, so the user can essentially activate e-mode without any particular constraint because the user is neither supplying or borrowing anything, so e-mode can be activated. If the user is borrowing something, we check here essentially if the category that the user is trying to set, because the user can also leave e-mode by resetting the category to 0 essentially. If the user is trying to borrowing, then we check is actually borrowing something. If he's borrowing an asset, we check that the asset is borrowing. It's the required line 692. We loop through the mapping essentially and check if the user is borrowing an asset, then that particular asset needs to be in the same category that the user is trying to essentially set. So imagine I'm trying to set category stablecoins and I'm borrowing stablecoins, then I am allowed to activate e-mode. If I'm trying to enter the category ETH, but I'm borrowing stablecoins, then I'm not allowed to enter e-mode because I'm already borrowing an asset that is volatile. So this is what it's being checked here. The advantage is that the user config is essentially one single UN256. So this for loop is essentially very, very cheap to execute. It could have been made cheaper by skipping areas of the essentially of the bitmap. Like we could have checked the bitmap in chunks, not bit by bit. But this made the code we tried. It made the code a bit too complicated, so we just left it. Like the gas cost, additional gas cost of this, especially if you don't have that many assets listed, is completely negligible. So we just left. We prioritized the easiness of code read in this particular case. So this is an example of how we use the bitmap within the protocol. There is also isolation mode that is also uses it more extensively because it checks if the user is borrowing. Isolation mode is another feature that we added in V3, and essentially it allows, like another problem that we found with V2 and we try to solve with V3, is that in V2 is really complicated to list assets and give them a collateralization factor. The reason is that there is no possibility to modulate exposure to that particular asset. So imagine, for example, that you try to list an asset in Aave V2, and you are giving collateralization factor to this asset. It means that theoretically, an entity that has access to a huge quantity of this asset could potentially borrow the whole protocol. In the worst case scenario, if it could happen, hopefully never happens, that there is a manipulation or something for which the user can borrow essentially the whole protocol. We had this problem in the past with the Sushi, because there was a potential risk for an Oracle manipulation that actually didn't happen because it was not profitable. But because we were unable to manage, we were unable in V2 to handle exposure to a certain asset, what could have happened is that because of an Oracle manipulation in Sushi, theoretically, there was a theoretical attack surface in which the user could have borrowed, an attacker could have borrowed the whole protocol, theoretically. So this was, of course, a huge problem. One, for safety, and two, because it limited the possibilities for Aave to list new assets. Because we cannot easily manage the risk, it's harder for Aave to list new assets as collateral. So we came up with this idea on V3 of isolated assets. So when an asset is isolated, you can only, when you supply an isolated asset in Aave, you can only borrow stablecoins in Aave, essentially, and the protocol tracks a very exact debt ceiling. So you can, in the configuration of the protocol, it's possible to say, okay, you know what, we can list this asset, but this asset is going to be an isolated asset, so only allowed to borrow stablecoins, and this asset will have a debt ceiling maximum up to 5 million worth of stablecoins. So we store this number, and every time a user borrows against this isolated asset, we check that we are still within the debt ceiling. If we go past if the user goes past the ceiling, then the borrow gets blocked. So this essentially solves the problem that, for example, we had with Sushi, because you can very precisely modulate how much you want to allow a user to borrow. These, of course, add some complexities because of the model. So we need to understand, okay, we need to figure out how to forbid users that are borrowing only one, that are borrowing using an isolated collateral to borrow different assets, because then in that case, it becomes impossible to track how much the actual user is borrowing. Imagine a user is borrowing USDC and ETH, for example. ETH is volatile, right? So you can never set an exact debt ceiling in dollars because the price of ETH changes continuously. And not only that, you could borrow ETH, you could borrow Rapid BTC. So it is impossible to limit the exposure in that particular case. So we had to reduce the use case to only stable assets, in this particular case, USD stablecoins, which is in any case the most common occurrence. So it's what usually happens is that a user borrows stablecoins. Like people borrowing other assets is a limited scenario. So this also brought some complexities, and essentially we had to handle this in a way where a lot of computation against that mapping was performed, because we needed to check what assets the user is borrowing, and we also needed to check if the user is only supplying an isolated asset. So when a user is trying to supply an isolated asset, like there was the question that we needed to implement. What we need to implement was, can we activate this asset as collateral or not? And this is actually in the supply function, and is managed in the supply function. I'm jumping a bit from topic to topic because they are very interconnected one to the other. I hope you guys can follow me.
Yeah, so we actually have a few meetings coming up now. Should we wrap it up here, and then we could?
Yes. For sure. I don't know. We can eventually, like in the future, talk about this. Even in the future more, if you guys are interested, we can.
Yes, definitely. I would love to do another episode, and because it's clearly a super deep protocol.
Yeah, there is a lot to unpack. So, and this some parts for me are also like sometimes I need to go back and check again the code because I need to refresh my memory. But at the same time, I hope I gave more or less an overview of how the protocol works, some ideas behind our design concepts, and like the design of the protocol itself, like advantages and trade-offs. And hopefully it was interesting.
Yes, absolutely. It's been super insightful. I'm trying to wrap my mind around it. There's so much depth going on here. But Emilio, thank you so much.